Hello students, welcome to the very next screencast. This one we're going to solve a quadratic equation, and it's going to be in a real-world setting. After a baseball is hit, the height, h, in feet of the ball above the ground t seconds after it is hit can be approximated by the equation h is equal to negative 16t squared plus 65t plus 3. Determine how long it will take for the ball to hit the ground. Round your answer to the nearest hundredth. Alright, so we know we need to round to the nearest hundredth, which is probably wise, otherwise we'd be writing digits forever. So what we need to do is recognize that what the situation is here is that the batter's going to hit it. The batter's right here. Right here. The batter's going to hit the ball, and it's going to form one of those parabolic arcs that we talked about in class. A parabola is going to be formed. It's going to be kind of one of those upside-down ones like we saw, but essentially think of it like this. So if the pitcher pitches it, and the batter hits it, it's going to form an arc like that, and it's going to land somewhere, probably in right field. Who knows? But as it does, as you can see, it forms that parabola. So basically, this equation here, which is a quadratic, because as you can see, the highest degree is 2, so the whole equation has a degree of 2, is going to make a parabola. And it's negative 16t squared, so it's going to be one of those upside-down parabolas. They don't make a U shape, they make an upside-down U shape, because it's a negative coefficient in front of the t squared. So the t represents time in seconds, and h represents the height. And this whole equation here represents the path the ball is going to take once it is hit. We have to determine how long it will take for the ball to hit the ground. In other words, from the batter to, boom, right there, say somewhere in right field. We got to round our answer to the nearest hundredth. So let's determine what we're solving for here. We have two variables. H is height and t is time. Which one are we solving for? Well, if it's asking us to determine how long, clearly they're asking us to figure out t, time, which means we need to know h. Alright, so let's read this again. How? I don't see a number somewhere in the text here, or even in this picture, that represents what h could be replaced with. Where can we take this h, remove it, and replace it with what number? Maybe there's clues in this problem here. After it is hit, can be approximated with the equation. How long will it take? How long will it take for the ball to hit the ground? Hit the ground, and h is in feet. So if this whole equation here, this quadratic, calculates the time it will take for the ball to reach this height, and we want the ball to go up, and then down, and reach a height of how many feet above ground represents the ball hitting the ground. We're going to take away h right here, and yes, folks, replace it with 0. We want to know how long it's going to take for the ball to reach 0 feet above ground. 0 feet above ground. I know that sounds weird, but 0 feet above ground is literally on the ground. And remember, one thing we said in class is that you can't solve a quadratic until it's equal to 0. Well, now, based on this, we clearly see that it has. And we could solve this quadratic numerous different ways. We've learned many of those ways in class. But I think a really, really effective way is using the lovely and always powerful quadratic formula. So let's do just that. We have to establish what is a, b, and c here. Well, it looks like a, which is the coefficient of the t squared, is negative 16. Please note that is a negative 16. And the coefficient of b is a positive 65. And c, the constant, is nothing more than 3. So now what we're ready to do is take these three numbers, negative 16, 65, and 3, and make sure that they get thrown in accurately into the quadratic formula. So let's take each number and plug it in. So let's get rid of this b. And while we're at it, why not get rid of this b as well, because they both represent the same number. That happens to be 65, positive 65. Ooh, we're going to have to square 65. That's going to give us kind of a larger number, which we'll realize in just a moment. Let's get rid of a, and let's also get rid of that a, because they both represent the exact same number. And as we saw here, it is negative 16, negative 16. So that's very nice. And then we'll get rid of this final one, this little c right here, and we'll see that that number is 3. All right, we're ready to go. We have our quadratic formula set up. Again, I say think about it in terms of three pieces. The first piece is this negative 65. Do what you can with that, if anything. Then take care of this larger piece below the square root sign. This is called the discriminant. You'll learn more about the discriminant as you take higher level classes of algebra, but it's very, very handy when you want to determine how many solutions does your quadratic have. Does it have one solution, which is possible? Does it have two solutions, which is typical? Or does it have no solutions, which it does actually happen? That is all determinant based on this, the discriminant. That's all these calculations, this number here, underneath the square root sign. And then the denominator, that's the third piece, 2 times negative 16. All right, so let's crunch some of these numbers. We see that x is equal to, well, the negative 65 can't change, so we'll keep it like that. Plus or minus, that plus or minus is important. It's embedded within the formula itself. 65 squared, feel free to confirm this on your own. 4,225 minus 4 times negative 16 times 3. Let's take care of all of this in one fair swoop. So negative 4 times negative 16. Well, we know we're getting a positive number, and multiply that by positive 3. Again, feel free to confirm that. It's positive 192 divided by negative 32. 2 times negative 16. Let's keep simplifying. So let's give ourselves some more room here. So we know that x is now equal to, well, still negative 65. Plus or minus, let's actually do the math. Remember, the square root is like a grouping symbol. It's like parentheses. You got to take care of what happens inside of that first. 4,225 plus 192 is 4,417, and we're still dividing by a negative 32. All right, so let's take what this is. We know 4,000, or at least we imagine 4,417 is not a perfect square. In fact, it is not a perfect square. So if we use our utilities to help us, we'll realize that the square root of 4,417 rounded to the nearest hundredth, as the instructions asked us to do, is 66.46, and we're still dividing by negative 32. Okay, at this point here, now that the square root is gone, we are able to consider this plus or minus to its full extent. So we're going to kind of make a split here. The first split is going to ask us to calculate what happens when you take x is equal to negative 65, and it doesn't matter what order you take that plus or minus into. Let's start with adding 66.46 to that negative 65 and divide it by negative 32 still. You get x is equal to negative 0.05, negative 0.05. Okay, so that's what happens when we add 66.46. What happens when we subtract 66.46? So we have a negative, x is equal to a negative 65 minus 66.46, and we're dividing that by negative 32. So we do the numbers first. We take care of the numerator, negative 65 minus 66.46, and we divide by a negative 32. You'll notice that the numerator is going to give us a negative number. The denominator is already a negative number, so we're going to divide two negatives and get a positive. That is a positive 0.411 seconds. That's 4 seconds and 11 hundredths of a second. And, you know, speaking of which, let's put the label on this negative 5 hundredths of a second. So now we have our two answers, but remember, there's this crucial component to quadratics when you're solving these real-world problems, is that you have to stop and consider which answer makes sense. Both of them mathematically are sound, but that's only in math. In the real world, certain things can and cannot happen, as we know. We wish more things could happen in our favor, but unfortunately that is just not always the case. That's what we call life. But one thing we can control is the fact that there's no such thing as a negative 0.05 second. There's no such thing as that. In fact, there's no such thing as negative seconds, let alone negative minutes or hours or days or months or centuries or years. No such thing as negative time. That doesn't exist in our world. So therefore, that answer of negative 0.05, no, throw that away. That's not part of your final answer. What is your final answer? Well, the ball is going to be hit, and it's going to take a little bit over 4 seconds. 4 seconds and 11 hundredths of a second in order for the ball to reach the ground wherever it lands. Which, I don't know. Is that right field? Is that infield? You tell me. Is that outfield? 4 seconds about? I don't know. You decide. All right, so that's the problem I wanted to show you. Nice job on that. Here, ladies and gentlemen, comes your problem, which you will solve in a similar manner. Your problem is about tire treads. The treads on the tire are those grooves and markings that help the tire grip the road better so that you, or the driver, has better control of the vehicle so that you are safer. A car with good tire tread, like this is good tire tread. As you can see, it's all nice, organized, symmetrical, not worn out like this, which can happen with tire usage. Good tire tread can stop in less distance than a car with poor tire tread. Well, that makes sense. If your car has tires that have better grip on the road, it's going to have a less stopping distance than a car with bad grip on the road. That just makes perfect sense. The formula for the stopping distance, D, in feet of a car with good tire tread on dry cement is approximated by D, that's the stopping distance, 0.04 V squared plus 0.5 V, where V, the variable V, is the speed of the car in miles per hour. All right, so we are in the customary system of measurement, miles per hour, not kilometers per hour. If the driver must be able to stop within 80 feet, that's important. What is the maximum safe speed of the car? Round your answer to the nearest mile per hour. All right, keep in mind what that means in the context of the situation. You want to round it to the nearest mile per hour. Okay? So that's your formula right here. Has to do with tire treads. Good luck. Email if you have any questions.